Give this one try. Is that okay? All right, great. So it is my pleasure to introduce Dr. Ryan Thigpen, who is also a good friend of mine, who we are. No. All right, never mind. So Ryan is a very good friend of mine, and he is a geologist by background. He got his bachelor's degree and his master's degree at the University of Tennessee. He then went on to spend a year, he then went on to get his PhD at Virginia Tech, and then spent a year as a visiting assistant professor at the College of William and Mary. He then joined BP from 2010 to 2015, which is where I actually met Ryan, and we discovered that we both were passionate about the Jackson Hole area, and that he was working on a side project on the Teton Fault with his wife, Summer, who's also a geologist. Right now, Ryan left beautiful Houston, I don't know why, to move to the University of Kentucky, where he is now assistant professor. And he actually started working on the Teton Fault in 2008, fetching rocks for his lovely wife, Summer, because she was working on the Teton Fault for her master's thesis. And he just got hooked, I guess. And so he's going to be talking tonight about whether the northern part of the Teton Fault was cataclysmically erased by the migration of the Yellowstone hotspot. So please, help me welcome Ryan.
Well, thank you, Cynthia, for inviting me, and the Jackson Hole geologists for having me. We're really excited to be here. And like Cynthia said, we've been working here for a long time. I actually started climbing here when I lived in Salt Lake City in 1999 and kind of fell in love with this place. And now we use this as our research escape every year. I'm sorry, let me ask, can everyone hear me okay? I'm wearing 2 mics already, so if I have a third mic and it's any of the quality of the one that Cynthia's wearing, it could be a painful evening for all of us. So we've been working here since 2008. So Summer started this project, the uplift project I'm going to talk about, where we're trying to date the age of uplift of this range. I sort of picked it up in 2015 when I went back to the University of Kentucky, and now it's getting really exciting because we have a bunch of faculty members at Kentucky that are bringing different skills and facets to this project. That's been a lot of fun. We have a whole heap of graduate students that are working out here, some outstanding students. I'm going to introduce you to them in my acknowledgments. So it's turned into a really large multidisciplinary effort. So every late July, August, including this year, when it gets really humid and horrible to be outside in Kentucky, we'll load up our wagons, literally, and drive out here and get to work. So we're spending a lot of time here. I mean, we absolutely love this place. So I had to start with this photo that my wife took out the window of the plane last night. I've probably flown in here, I don't know, 20 times, and I've never seen a view like this when we hooked around the mountains, and it was a lot of fun. I've got my parents with me. We're on a 2-week Western road trip, so I promised them good views. So we've been on all the Pacific Northwest volcanoes. We've been to Yosemite. Last night's flight in here might have been the prettiest part of this whole trip. So let me see. I'm coming unwired here. All right. So I'm sure most of you are already aware of this, but the Teton Fault is what controls the uplift of the range, right? So grab my pointer here. So I've got a little 3D block model here showing that uplift. It's a big normal fault, which means we have the hanging wall here in the Jackson Hole Valley dropping down to the right. We've got the footwall being uplifted to the left. This footwall uplift component is going to become very important to the analysis we're doing, and the location of that block is sort of shown here. What's so incredible about the Teton Range is that when we first came out here, we really didn't understand what its genesis was, because it sits at the confluence of a whole bunch of geologic provinces, right? You guys know about all these, but we've got the severe fold and thrust belt down here, the Meade and Absaroka and Prospect thrust, the Darby. We've got these weird laramide thrusts, like the Cache Creek thrust, and then the laramide uplifts, like the Wind River Range to the south, that none of us, no matter how long we study this thing, can seem to come up with a great explanation for why we have these big basement chord uplifts in the middle of nowhere. As a matter of fact, on the way from Portland, Oregon down to California when we were driving, I turned to my wife, who's worked here a lot, and said, "Do you know what causes the Grovant uplift?" And it seems that nobody does. So if anybody has a great explanation, I'd love to know what causes that. We've also got the Yellowstone hotspot up here. And of course, this whole area, this larger area, is part of the Basin Range. So this is this sort of recent, last 20 million years extension of the American West that causes all the mountain ranges and basins you see in places like Utah and Nevada. Here we think we're sort of on the very northeastern corner of that area. I'm going to try to convince you tonight that the Teton Fault is quite a bit older than most people think it is. And you may not be convinced at the end, but hopefully we'll get some spirited discussion out of it. But despite being sort of old, it still remains active. So I imagine some of you have probably seen this data before. This is the National Park Service LiDAR data set. It came out in 2014 and completely changed everything. I wasted somewhere around 4 to 6 days of my life looking at this data when it first came out because it's so incredible. You see everything and you want to look at it. So this is up at Bradley and Taggart Lake. You can see these spectacular moraines with the retreat terminal moraines. And then you can see, of course, my old advisor used to say, if you can't map the fault here, you should go back to farming. It's a really spectacular exposure of this fault. And we can see these offsets. So these offsets are in meters. We've got 27 meters of offset on this lateral moraine, 12 on the post-glacial. This is 12 meters of post-glacial offset. Now we're assuming these glacial features, as Ken Pierce and Joe Licciardi have done a great job of documenting, are probably about 15,000 years old. This is an incredible rate of slip, right? 12 meters of slip. The more interesting thing, perhaps, though, is that the slip events that we've been documenting in the trenching studies that have been done by folks like John Bird, Bob Smith, Mark Zellman, Glenn Thackeray. I didn't mean to leave him off here, but Glenn Thackeray at Idaho has done a bunch of this trenching work. These are big rupture events, 1.3 to 2.8 meters. But what's even more interesting is that we only have a couple of them in the section when we do these trenching studies. So we've got 12 meters of post-glacial offset, but we're only documenting about 4 or 5 meters of it in the trenches, which means that we're missing about 7 meters of the record here. Now, I'm not going to belabor the earthquake point, but I am going to talk at the end about what our team is doing to try to fill this seismic gap. In the Himalayas, they have a similar seismic gap. It's bigger than this one, but they're missing about 10 meters of slip. And if they can't find those events, then they have to plan for sort of a magnitude 9 slip event. A 10-meter slip event is a huge slip event. So finding these slip events, wherever they're hidden in these trenches or in the lakes, is critical to the work that's going on out here. And there's a lot of people doing this. USGS just dug a big trench at Buffalo Bowl to try to resolve this issue. And even though I haven't seen all the data coming out of it, I did get to have beers with those guys back in December, and it sounds like the mission is still not accomplished. So we have some challenges. All right. So the idea I'm going to talk to you about today is the idea that the Yellowstone hotspot, which sort of has tracked across this mountain belt, I'll call it a whole bunch of mountain ranges, this large mountain belt that extends all the way from Mexico all the way up into northern Canada. This is the only place where that topography has become subdued. It looks like a giant pencil eraser sort of moving across the mountain belt, right? So what's happening here? Well, I'm going to use the term, you're going to hear me say the term over and over again, migration of the Yellowstone hotspot. It sounds like the hotspot's moving. It's not actually. It's the plate moving over the hotspot, and so this hotspot, which once again, even some volcanologists argue over why exactly these hotspots localize, but this is a big hot mantle plume, and it's sort of poking up, and the plate is sort of sliding over the top of it. You can think about it like holding a lighter and running a piece of notebook paper across the top of it. You're going to just sort of burn holes in the paper. And so what's actually happening is the hotspot's remaining fixed, and the plate itself is sliding in this direction, and it's marking this track. And so we can see we had the Twin Falls eruption about 10 million years ago, Picabo the same, Heiss about 6.4, and now we're in the modern day. This red outline here is actually going to be Huckleberry Ridge, and then we've got this modern hotspot here. And the idea I'm going to try to sell you on is that all of these mountain ranges have been erased by this hotspot, that these mountain ranges used to exist, these big faults used to continue across these zones, and that the hotspot itself has erased this topography, that the topography has essentially collapsed into this caldera as it's migrated past. Well, the great thing about the Teton Fault is it's one place in the world that we might be able to prove this. And I say, I'm going to use the term prove very, very loosely, because I'm going to show you some evidence that I think is incredibly convincing, but it's not definitive. And I'll be interested to hear what you think about it. So like I said, a project like this can't be done without a whole bunch of people, a lot of money, and a lot of help. And so these are my colleagues. Summer you've met, she's back here, that started this project. This is the really miserable view we have to endure off of Cynthia's back porch when we come to visit. This is Professors Mike McGlew and Ed Woolery. Mike is a paleolimnologist. He's a lakes guy. He's an expert at coring lakes and shooting seismic on lakes. Ed Woolery is an earthquakes guy that also does a lot of 2D seismic reflection, so imaging on the ground instead of in the lakes. Those things are going to become huge pieces of this project. Joe Lucas's job, his only job, was to drive the boat in a really straight line, which turns out to be a lot more challenging on Jackson Lake than other places that we work. I had two excellent graduate students. I don't know why they're doing this pose, but I had to catch it, that have recently graduated working on this project. And Professor Willie Gunther at the University of Illinois has been doing all of our thermochron analysis. So we pick the grains and send them to him. The Park Service has been super supportive with permitting. The University of Wyoming National Park Service Research Center has funded some of the seed parts of this work and has given us excellent accommodations. And we've got numerous small grants from smaller grant agencies like GSA and AAPG that have been given to graduate students to sort of keep this project afloat. All right. So there's four things I'm going to try to convince you of, and one thing I'm going to speculate about. Actually, I'm probably going to try to speculate about a bunch of things, but the first thing I'm going to try to convince you of is that the Teton Range started moving somewhere around Mount Moran about 17 million years ago. So it's quite old. It's probably a basin to range structure, and because of that, most of the uplift that happened across this range happened before the Yellowstone hotspot arrived at 2 million years ago. The second thing I'm going to try to convince you is that the maximum displacement at Mount Moran, which we consider to be sort of the paleo center of the Teton Fault, is about 9.4 to 12.7 kilometers. It's a big crustal fault. Using those displacement estimates that we've derived from our uplift studies, I'm going to try to convince you using fault scaling relationships and fault mechanics that this fault is actually was 155 to 210 kilometers long, so substantially longer than what we see in the present day length of the range. This is where things are going to get speculative. I'm going to try to convince you that this mountain range disappeared into this caldera, and perhaps the other mountain ranges along this track, making it one of the fastest topography removal mechanisms anywhere in the world. The last thing I'm going to try to convince you of is that the fault may remain active beneath the modern Yellowstone hotspot. Now, this is something that's just some data that we're just starting to put together. It's very circumstantial and none of it's proven, but I'm going to show you the work that we're going to try to do to, I won't say prove it, but to improve our understanding in the northern part of the park. Okay, so some terminology. I've tried to make this as accessible as possible. It was impossible to remove all the terminology, so I've put the important bits in here that I think you need to know. So here we've got sort of a cross-section of the Teton Range. We've got the Teton Basin over here in Idaho with our sedimentary fill. And here's the Jackson Basin. This is all sort of exaggerated, but we've got the Jackson Basin with all our hanging wall fill. Here is the normal fault here. And so there's sort of three components to this. The greater displacement is the total amount of slip on the fault to include both the uplift of the footwall and the drop down of the hanging wall. Now, when normal faults move, crustal scale normal faults, when they move when they extend, what happens is we're changing the thickness of the crust underneath the fault. And when we do that, we're allowing the mantle buoyancy effects to take over. And that mantle buoyancy effect is going to drive our footwall uplift. Now, the magnitude of that uplift is a function of a whole bunch of things that I'm not going to get into tonight, but I'm happy to discuss with you if you'd like to talk about it. But that footwall uplift is what we're actually measuring. So what we're going to do is we're going to use a technique called thermochronology to measure the footwall uplift, and then I'm going to take that footwall uplift with some models of how these normal faults grow, And I'm going to use that footwall uplift to predict how much displacement has occurred on this system. And then I'm going to take that displacement and use it to predict, based on empirical scaling relationships, how long the Teton Fault originally was. Sorry, not is now, but was. Something else that you might hear me talk about is how the footwall gets eroded. So the footwall that we see today, the popped up footwall that we see, is actually the minimum amount of footwall that we have, right? Because a lot of this has been eroded, and all of you have driven across the front of the Tetons. I don't think I have to convince you of the erosion. And we'll talk about the erosion tomorrow if you come at noon specifically. Okay, so I'm going to try to make this as simple as I can. So we're using a technique called apatite, uranium, thorium, helium, thermochronology. It's a big pile of words. What it basically means is that we have these minerals, these little apatite grains. These are in the rocks. Apatite is actually the same mineral that your teeth are made out of, so technically we could get a helium age on your teeth, I suppose. When these apatites form, they incorporate small amounts of uranium, samarium, and thorium. In the uranium decay series, these things are spitting off as a byproduct helium as they decay at some predictable rate, right? When these grains are buried deeper than 70 degrees C in the earth, the closure temperature varies depending on rates and all these other things, but it's about 70 degrees C. When they're hotter than 70 degrees C, all that helium leaves the grain, okay? When they get closer to the surface, a couple kilometers closer to the, or within a couple kilometers of the surface, and that grain cools below a temperature of 70 degrees C. Sorry, that says above 70. It should say below 70. When they're cooler than 70 degrees, that helium sticks in that rock. It stays there. So if we can measure the amount of uranium and thorium and samarium in this grain, and then we can measure the helium, and we know how fast that helium is produced, then we can come up with an age at which that grain came through what we call the closure temperature, or that temperature where the helium starts being captured. And this allows us to put dates on this sort of upper 2 kilometers of evolution that's happening in the crust and date the uplift of this range. So the way that we do this is we actually use a whole stack of these grains. So you could imagine if we have one of these grains, and we're going to be looking right here, and it's traveling towards the surface, it's cooling and cooling, and eventually it makes it to the surface, and it's going to have recorded this closure temperature window, the time that it went through this closure temperature window, right? If we collect a whole bunch of these grains at different elevations, say climbing up the east face of Tiwanaut, then we can actually see how those ages change with elevation, and that is our proxy for depth. So if we start up here at the summit with this blue sample, we're going to have the oldest age up there, right? Because the oldest grain is the one that came through the closure temperature first, and it's now at the highest point. That low grain, that one in the parking lot at Lupine Meadows, that grain came through the closure temperature last. Its age should be a lot younger. So we should expect with elevation as we decrease for those ages to go from old to young. And if we're lucky, we'll actually see an inflection point in those ages that shows us where we went from some sort of background background exhumation to rapid uplift. And that's a lot of times what we see. Now, it's not always that simple that we can make an age elevation plot and say, okay, that's where the fault, that's the age at which the fault started moving. So what we actually do is we use the numerical modeling package that allows us to put in this data, and we can put all this data into the model, and then we can run a bunch of scenarios that allows us to determine what's the most likely scenario that this data matches these uplift histories. And so that's what we did. We started doing this in 2008. So this is 2 children at the Boise house in 2008, so 11 years ago. This was a descent of Mount Moran. This was one of the most interesting descents. I've never rappelled 1,000 feet with 30 kilos of rock in my backpack. Probably wasn't 30 kilos, it was a lot. It was heavy. It's very, those down climbs get a lot sketchier. And then, of course, paddling our canoe across the lake. So we came out here and we started by collecting 3 transects. So we started at Mount Moran, we collected one at Grand Teton, we collected one at Rendezvous Peak. And those transects, for any of you that might have read the paper, maybe you didn't, but Summer wrote a paper in 2017 that described those transects that was discussed in tectonics. So I'm going to augment those with some new modeling and some other stuff. We've also collected a transect at Eagles Rest. My student, Rachel Hoare, who just graduated, she and I collected that transect a couple years ago, so I'm going to include that data. But the way these things break down, you can actually see we've got young ages at the bottom. So this is the Grand Transect, about 11 million years, 6.8 in the parking lot at Lupine, so about 7 million years. All the way up to about 35 million years. We've got some weird inversion stuff going on up here near the summit. At Mount Moran, we start about 7 million years at the base, about 20 million years at the summit. I put these other 3 transects on here because I think they're really important. These are the ones we're working right now. We've collected a new transect at Rendezvous, a new one at Static Peak, and a new one at Teton, and we're analyzing that data. We don't have many of that data available, but we're hoping Teton will tell us a better story than the Grand did because it's closer to the approximate fault plane along the range. Okay, so these are those models I talked about for the 4 transects I'm going to discuss. So we've got one transect at Rendezvous, there's the Grand, Mount Moran, and Eagles Rest. And what you're looking at here, you've got the samples going from low elevation here, the sample at the greatest depth to start to the high elevation samples. And so what this software is trying to do is to take all these samples and their elevation spacing and try to find a time temperature history that best fits this model. We can also output what this model predicts and compare it to our observed data. And the observed versus predicted, if you'd really like to see it, I can show it to you. They were really gorgeous fits, actually. But what we see is that we've got an uplift onset. You can see that uplift, these samples starting to cool about 11 to 9 million years ago at Rendezvous, about 12 to 10 at the Grand Teton. This is our really old age at Mount Moran, but it was also our best model. This was an outstanding model from a thermochronology standpoint. It was about 17 to 16 million years ago. And then at Eagles Rest, modeled uplifts about 9 to 7 million years ago. I have less confidence in this model. We have way fewer samples than we'd like to have, and so this could be refined over time. The other thing that I have on here, I have the eruption events from the Yellowstone, this Huckleberry Ridge, Mesa Falls, Lava Creek, and you can see these are happening at the very end of this uplift history, so they're just shown there for reference. Okay, so this was my first point that I was trying to convince you of, and I may not have because you may not believe my models, but this uplift we think started about 17 million years ago. Okay, so now I'm going to try to explain to you how we determine what the displacement is so we can determine the length of the fault. So the way that we do this is, I told you about the closure temperature that we have in these systems. Well, it turns out that that paleo closure temperature, or where the closure temperature used to be, can be recorded in our transects by finding the break between the samples that are older than when our fault started moving and the samples that are younger than when our fault started moving, identifying what that elevation change is, and then projecting this closure temperature into the ground. So if this is the modern day closure window, a couple kilometers deep in the earth, and here is our paleo closure depth, we can come up with the difference in distance between those two things, assuming that there hasn't been a major change in geothermal gradient or the temperature change with depth over time. And so at Mount Moran, to do this, if we assume that it's about 1,300 meters of elevation from the base of the transect up to that paleo break that we see between these two ages at about 3,400 meters, and then we assume if we have a closure temperature of about 70 degrees C and a gradient of 25 degrees C per kilometer, which we derived from a study here in 1987, then we get a depth of 2,800 meters from the base of the transect into the earth to the actual closure temperature. If we add those two numbers together, we can come up with a footwall uplift at Mount Moran of about 4.1 kilometers. Okay? So this is phase one. I know it's a little complicated. It's this. I struggle to explain this every time. I struggle to explain this to myself sometimes. Okay, so let's go back to our 4 transects. There's the ages of uplift that we talked about. And now I'm going to put the footwall uplift on each one. So you can see at Mount Moran we've got about 4.1 kilometers of footwall uplift. Interestingly, at the Grand we've only got about 3.2 kilometers. Rendezvous about 3.1. I will admit that this number has some uncertainty in it because of the way those samples were collected, and like I said, we're hoping to improve this with our Teton transect we collected a couple years ago that's still in progress. And then over at Eagles Rest about 3.5 kilometers of uplift along this transect. Well, if you take a simple model of how faults grow and you think about how these things, if they start in the middle and they sort of tip propagate their way out, or maybe they grow a whole bunch at once and then they grow by constant length displacements, but eventually they have to get longer. But either way, the way that faults should predictably grow is that somewhere near the center of the fault, they don't have to be perfectly symmetrical, but somewhere near the center, you should expect to find the most offset or the most uplift and the oldest age of motion, right? And so seeing this leads us to suggest that Mount Moran was actually sort of the paleo center of the Teton Fault because it has the oldest uplift timing and it has the most uplift. Now what was interesting this morning actually while we were out on a boat taking samples, Bob Smith sent me a really beautiful figure from one of their Wyoming Geological Society papers that showed that the modern scarp actually has the modern scarp actually has the most offset at Mount Moran, and I actually didn't know that because we haven't done a lot of analysis of the modern scarp, but that's, I say, hooray. That's a good thing. So right now we're interpreting Mount Moran as I'll call it the center of the Paleo Teton Fault right now. I won't call it the main Teton Fault, the Paleo Teton Fault. Okay, so now this is going to get even more nebulous, but there's a whole bunch of models about how much of the total displacement is footwall uplift, which is this guy, and how much of it is hanging wall drop, which is this guy right here. But it doesn't really matter what parameters you use. If you use any reasonable parameters, say 20 to 60 degree dips, which we think are really reasonable for the Teton Fault, the right flexure parameters for the crust approximately, it doesn't seem to matter what knobs you turn. You always end up in sort of 32 to 44% of total displacement being footwall uplift, right? So if we take these footwall uplift estimates that we've derived from Chronology and we put them with displacements, we can come up with a displacement on the fault. And so at Rendezvous Peak we get about 9.4 to 6.1. This range represents the difference, the different percentages that we get from different models. We've also run this simulation with a higher geothermal gradient to account for Yellowstone, and it decreases the offsets a little bit, but nothing crazy. 9.8 to 7.2 at the Grand, 12.7 to 9.4 at Mount Moran, 10.8 to 8 kilometers at Eagles Rest, so pretty decent size amounts of throw. I should say that we've used a even higher closure temperature system, a system that closes at 110 degrees C. So these are samples that are coming from very deep, from 5-6 kilometers deep. Those samples are very young at the base of Mount Moran. We've only published a little snippet of that data. We haven't published all of it. So those ages really back up what we say here. Okay. So that's our displacement. So now I'm going to take that displacement and try to show you how we think it lengthens the fault. If this fault grows by segment linkage or tip propagation, which is how most normal faults grow, then this is applicable. Now there's another model called constant length evolution. Constant length evolution means that a fault, either because it's taking advantage of a pre-existing weakness or because it has a major earthquake, will break really long, and then it can accumulate displacement without getting any longer. But eventually, if it's going to continue to accumulate displacement, it has to lengthen. So even the constant fault evolution models can't explain this away, if you will, what we're going to talk about. So this is a graph of faults from 10 to the minus 3 in length all the way up to, as long as we get, hundreds of kilometers long. And this is every fault measured in all of these data sets. These are a whole bunch of normal fault data sets from all over the world. It's funny, actually, I actually had this idea when I was at BP working for someone, a supervisor, not a supervisor, but a mentor that Cynthia put me with that was really sold on these fault scaling relationships. And he kept saying to me, It doesn't matter what you think about the length of a fault or where a fault is exposed. It matters what the physics tell you. And that's really important. This graph shows that no matter what length the fault is, no matter what substrate it cuts, no matter what the parameters, these normal faults are following a very clear scaling relationship. Okay. So I'm going to take you through this. So this is a little zoomed in model. So this is our tip propagation model. So you can think about this as the fault lengthens, the displacement that it must accumulate will increase. This is our constant length fault evolution model where we accumulate a whole bunch of length and then we can actually grow back into sort of equilibrium with our tip propagation line. But if we take the traditional length of the Teton Fault, it's about 65K. And we plot it on this graph, we get a total offset, total displacement of about 3.9 kilometers. Unless we have an incredibly high geothermal gradient under this range, which Heisler's study in 1987 sort of shows is likely not true, it's impossible for our samples to have these ages and have only 3.9 kilometers of offset. Okay? And I want to point out too that this dashed line I've put here, this is our what we call the 0.06 line. This is the most conservative estimates. These are the shortest faults possible for a given displacement along this dashed line. If I put my base case model in there that I just showed you, 9.4 to 12.7 kilometers, I can have a fault length of 210 to 155 kilometers, and this is where we came up with this number. And once again, I want to highlight that we're using the absolute most conservative estimates for this. These green guys right here are in a study by Densmore et al. In 2004 where they're looking at basin range faults, including the Teton Fault. And the only reason the Teton Fault's not plotted here is because Densmore used the wrong displacement for the fault. But these are basin range faults. If we followed that blue line, you could see I could slide my little base case model over, and we'd be looking at a fault that's even longer. So this is the most conservative estimate that we have. And so what does that look like? Well, we sort of just plotted up on the map. We said, okay, we've got some complexities down here with the Cache Creek Fault, and I'm sure someone's going to ask a question about that. I hope they will, and I'll talk about that when that time comes. But if we just take that length and we cut it in half, we say 75 to 100 kilometers north of Mount Moran, which we consider to be the middle, which is about right there, then this is what it looks like. So 75 gets us just up to Yellowstone Lake. 105 gets us even north of the lake, and so our idea is that this area inside this purple box, maybe this purple box, maybe the whole purple box, was actually part of that fault, had this big uplifted part that dropped into the Huckleberry Ridge caldera and possibly even into the later caldera eruption events at 1.1 and 0.6 MA. But the Huckleberry Ridge one we think was the big killer of this topography. And you can kind of see where the topography goes down and it sort of runs right into the boundary there with Huckleberry Ridge. So sort of a way to think about this would be our regular traditional length of the fault. Here's those estimates shown. And so this is the way that we're projecting it. 75 kilometers north of Mount Moran, 105 kilometers north. And I always like this figure because this is all drawn to scale even with some vertical exaggeration, but these fault profiles don't look like anything that any of us mapped when we had really good data, say in the Gulf of Mexico or somewhere else where we're mapping normal faults. All right, so that was my next conclusion. We think the fault used to be pretty long. The last part, this is where things get really conjectural. So this is a figure I actually found that I poached from Lippmann 1984, where they talked about caldera collapse and how it actually happens. But the idea here, the simple idea is that you get all these eruptions, you get all this magma and the phreatic eruptions and the Plinian columns, all the ash fall, everything. And when the eruption is coming to its end, you've run out of material underneath the caldera to support it. And the caldera itself just collapses into itself. And so you can see these green bits used to be that pre-existing topography, and it's all fallen into the caldera. This idea was actually proposed by Ruppel in 1972 and by a USGS geologist named Christensen in 2001. They proposed that some other mountain ranges, I think Christensen actually proposed that an extension of the Gros Ventre Mountains actually went through Yellowstone. They hypothesized that this could be the case. So this is not a new idea, but we do think we're starting to find more data to support the idea. But then the process starts all over again. You get another plume rising, you uplift this thing and this collapses over and over again. Of course, Yellowstone, modern day hotspot, it's collapsed there, 3 times we think. So, okay. So the last thing I'm going to try to convince you of is that maybe some remnant of this northern extension continues north. Now I have to say, being a structural geologist and understanding things like brittle versus ductile deformation, et cetera, my belief is when that hotspot comes through, it basically erases most of this fault. It's so hot that you can't really have a good brittle fault there anymore, right? It's not something that's easy to do. So the hotspot changes the whole rheology, the way the material behaves in this zone. But what's interesting to think about is whether or not some piece of it still continues north. And so we'll go back to that LiDAR data set. Once again, a beautiful exposure of the Teton Fault scarp. There's about 13 meters of displacement across it. Hilariously enough, you can see this very clear in the LiDAR. I've been to Wilcox Point and had a hard time finding this outcrop on the ground. So it's really incredible what LiDAR is doing for us. But if we just sort of project this north, we go into the lake, that's a problem. But we have some interesting features on the other side of the lake. These have been identified by other people. As a matter of fact, Glenn Thackeray and Mark Zellman and some other folks have already trenched this structure over here. This is the Steamboat Fault scarp. I don't know if this one has a name. We're calling it Fonda Point, another scarp over here. But what we did is we came out with our team last year and shot seismic reflection of the northern part of this lake to try to link these segments up. And so what we ended up seeing, I'm going to show you the seismic in just a minute, was that there's actually an antithetic and synthetic fault system that crosses the lake, and it ends up over here sort of at Fonda Point. But our seismic data, we have these 3 lines, sort of fell apart here. We're speculating that what happens is that this thing is linked through some sort of linkage relay up to where the Snake River Delta is entrenched, and then it comes over here and joins the Steamboat Fault segment and continues north. These are things we'll be investigating this summer with new studies. But if we go off the right side of this page, we're going to show up over here. There's our Steamboat Fault segment. It's a gorgeous fault segment. We hiked a bunch of students out here. You could tell a lot of elk had been sleeping here, so we nicknamed this segment the Elks Lodge before we knew that Thackeray's group had called it the Steamboat Mountain segment. But we've sort of projected where it goes through here. There's a big, beautiful landslide here on Steamboat Mountain. And then there's another creek that's been diverted, and we think this may be another piece of the modern day scarp that's actually sort of beheaded this stream right here. So this is our lake profile. You can see these gorgeous exposures. That's the Teton Fault right there. In the lake, it's only got about 2.1 meters to throw. This is excellent for us, because this means that maybe in these sediments in the hanging wall is recorded the other slip events, the record that we've been missing all this time, the 7 meters or whatever of record that we're missing. So our team will be coming out this summer to shoot a whole bunch more seismic lines. And I've lost a slide here. We'll be shooting a whole lot more seismic lines to better constrain this zone. We're going to do a side scan sonar survey, which allows us to see what the lake floor looks like, see what the high resolution bathymetry looks like. And we're also going to be coring, and I think I have a slide that shows that in a minute. All right. The last idea, though, so this is our Dime Creek segment here, that last beheaded segment, and then we lose it in the modern Snake River Plain. And then in the LiDAR, there's a whole bunch of faults over here, and I think Mark Zellman just published a map of the LiDAR through the Wyoming Geological Survey where he shows these segments, and he talks about, I think he calls them the Huckleberry Springs fault system or something. And so we've sort of wondered if these are the buried segments of our old fault covered by these lava flows now. But you've got some ground rupture. You can see that sort of linear ground rupture, but you've also got the only hot springs in southern Yellowstone, right? So it's interesting. Maybe the faults are localizing this. The other thing that's really interesting, I'm going to ask you to sort of squint your eyes. I may have had too many glasses of wine the night I came up with this idea. But if you look at these, earthquake trends in Yellowstone. This data is from Huston Smith and was presented in White et al. 2009. You can see some sort of linear patterns of earthquakes that seem to diverge. This white box right here is this box that sort of diverge from that zone where we're projecting the fault. Another interesting little tidbit, I had a student collect a transect in the Teton Range fault in the north part of Yellowstone a couple years ago, and this is the uplift age that we came up with for the Gallatin Range. So maybe the Gallatin Range is not linked to the Teton Fault, but they're on the same trend and they have almost the exact same uplift age. So it's very interesting. There's still a lot of work to be done there. So what we plan to do is to come back this summer. We're going to shoot some test seismic lines where these orange guys are, some seismic reflection profiles, to figure out what the substrate is. The substrate up here is really complex. It's highly variable, and we have to figure out the best way to image this thing. But once we do, we'll be coming back next summer with the USGS Intermountain Hazards Group to shoot this long seismic line shown here in yellow to see if we can image the deep Teton Fault here, or at least the shallower parts of the deep Teton Fault. Okay, last thing, we'll be coming back. We'll be doing some of this stuff in July and August of this year. We're going to core some of these segments of the fault. We're also going to do some test shots across some of these segments where there's not a really perfectly exposed scarp to see if there's anything that we can see. So this project is really just getting off the ground. Actually, today we were out with Dan, on the boat with Dan. Dan was helping me do drop sampling. We're trying to find the right places to core. We can't core through sand and we can't core through the gravels. So we're looking for the good muds, and we found lots of good stinky mud today along some of these transects. All right. And then this is a zoom in of where that line's going to be. So this is Flag Ranch, the water treatment area at Flag Ranch, and of course this is Grassy Lake Road or Grassy Cove Road. But you can see those fault lineaments there, and so we're hoping that this seismic line will we hope will either confirm or deny that that the fault continues north. If we do find the fault here, then we'll be thinking about what comes next. All right, so the last thing is to think about, well, if this works, if we end up making this work up here, we really have to think about, can we do a similar study with some of these other structures, see what the age these mountain ranges are, see if they are quite a bit older than the migration of the hotspot through the zones, and sort of prove the idea that the Yellowstone hotspot has acted like a giant pencil eraser, just erasing this topography that, like I said, that's breaching a range of mountains, or a belt of mountains that goes all the way from about Monterey, south of Monterey, Mexico, all the way into northern Canada. And with that, I'll take your picture. I think this is 399's cubs, and my wife, who's an incredible photographer, caught this picture when they all took off running. But it was pretty incredible. So thank you for your time.
Questions?
Oh, look at the bears.
All right, I'll get you started.
Okay, John, shoot.
On the imagery you pulled out of the lake, what would you estimate the dip angle on the Teton Fault?
We're getting about 60.
About 60?
Yeah, which is pretty similar to the scarps, the modern day scarps on shore. But I mean, I'm always skeptical to take the really shallow surface expression, particularly after what I saw today when we were sampling. I mean, it's all mud, so the lake muds may behave differently than the brittle bedrock. I think we've talked with USGS about, while we have our Vibroseis and our 360 channel system out here next summer, we've talked with them about shooting a line in the center of the range where we know the fault is, say at Lupine, somewhere maybe near Tiwanaut. And we've got to have those discussions with the Park Service, because it's a long line. We'll have to close roads. But for I'm not a paleoseismologist, but for the paleoseismologists that work at USGS that do this work, the dip of the fault is critical for their hazard analysis. And so, be great. Yes?
You said you might comment on what happens on the south end here.
Yeah. So I think I think of it like an airplane wing, right? Like they make them out of a bunch of different pieces so the fractures can't propagate. So the Teton Fault comes south and it hits the Cache Creek Fault, which we know to be a laramide structure, so it's quite a bit older. I think it almost gives it like a free boundary so that it doesn't really have to obey that southern fault relationship. If the crust is undeformed there, I think you would expect to see that fault continue. But I think that hitting the Cache Creek thrust there makes it actually stop. but still allows it to accumulate displacement. So in that scenario, we would expect the uplift of the range at Teton Pass, even though it's very close to that tip of the fault, to probably still have a few kilometers of displacement. And I think, when you drive over the range into Idaho, you can convince yourself that there's definitely still some displacement. But that's a little bit of a punt because we don't know what the structure is down there exactly. And so we've talked about having a student get in there and do it at sort of the quarter quadrangle scale, a tiny scale, to really map it out. And that may be a future EdMap proposal. Because Love did a lot of great mapping down there, but he had a huge area to cover. So it might be good to have something smaller down there. Yes. Sorry. Yeah.
Thank you. I'm a college professor, and I always encourage my students to ask questions, even if they think they're stupid questions. And so therefore, taking my own advice, I'm going to ask you, could you characterize what is a hotspot? What do you know about it?
Oh, gosh. I might need a drink. So I imagine there's probably some brilliant volcanologists in this room somewhere hiding that would be better at this. I've watched guys at conferences argue about this. They just seem to be sort of mantle anomalies, places where we're getting a lot more heat flow from the mantle. Summer actually teaches a class in volcanoes and earthquakes. Maybe I should let her answer. But the other day I called it the plume, and she said, well, Ron, it's not the plume. You're talking about the magma. The plume is the heat. And it just seems to be a really hot spot in the mantle that just sits there. It's kind of like Hawaii. The Hawaiian island chain is a result of this weird mantle anomaly just sitting there burning a hole in the Pacific plate. And I wish I had a better explanation for you. It's weird.
It's about my level of understanding.
Okay. Yes. So sorry.
Now that we're on temperatures, can you explain to us just a little bit about the thermal gradient that you talked about there?
Yep.
Temperature versus depth. Is it uniform over large areas, small areas? And how do you
The Heisler studies seem to suggest that at least in this basin, in the Jackson Basin, that it's probably fixed. Now, the caveat to that is that we don't drill, we don't have a bunch of deep wells here. So this is all shallow data that we're looking at, but a lot of it too is based on surface heat flow. So if you make some reasonable estimation of how thick you think the crust is and how much heat is being produced in the crust, then you could probably come up with some estimate based on the surface heat flow of what you expect the geothermal gradient to be. 25 is pretty standard for continental crust. Heisler's the guy that worked here. I apologize if I'm saying his name wrong and somebody knows who this guy, Hessler, sorry. He came up with about 18 to 27 degrees, so we use 25 per kilometer. We also, in the calculations we've done for a paper that we're writing, we used 40 as well to sort of say, okay, maybe it's warmer because of the Yellowstone hotspot, but remembering that the hotspot gets here quite late. So maybe it doesn't matter.
But those temperatures that you plot versus depth, those are all extrapolated based on that uniform heat gradient.
Well, our models actually allow for advection. So it starts out uniform, but when the mountains start moving, it accounts for advection. So it's accounting for heat moving. Rocks are notoriously poor conductors of heat. So when rocks move quickly, they don't get rid of their heat very fast. So it accounts for that as well. John, Mike, sorry.
Yeah, so if Mount Moran is the center of the fault and the greatest displacement there, how did the Grand get to be over 1,000 feet higher than Mount Moran? What mechanism is...
Well, I think there's a lot of complexities in that. So a guy named David Foster did a big study here in 2008 where he called Mount Moran and the Grand, he called them Teflon peaks. They're basically these super tall peaks that stick up around everything else. But when you look at the drainage morphology around those zones, what controls erosion in the Teton Range is really frost wedging and talus production, rocks breaking down, right? And I'm going to talk about this tomorrow, but most of the rivers in this system are not strong enough to move these big, huge chunks of rock, right? So what's controlling a lot of this is when the glaciers come in, and where the glaciers localize, where those drainages are, greatly controls the erosion you get in the range, and it controls the oversteepening of the drainages, which also controls the landsliding that you get to drive most of this stuff. The other thing I was sort of struck by, I've just recently been getting into surface processes and erosion and stuff. I'm working now in the Himalayas, and I went to Langtang in the Himalayas right after the Gorkha earthquake in 2015, and I was shocked by how much of the erosion happens when you get one earthquake event. All the erosion's happening in like a 0.00001% of the time. And so the erosion story to me and how the topography evolved seems to be so much more complex than the simple tectonic forcing, I think would be my answer to that question. So there's a lot of other factors at play. We do know that the top of Mount Moran, even though at an equivalent height of the Grand Teton, our samples are younger. So they've come from greater depth from that equivalent height on the Grand. Yeah, so if you take one of our samples on the Grand Transect, it's about the same elevation as the summit of Mount Moran. The ages at Mount Moran are younger. The top of Mount Moran in our transect is 20 million years old. About that equivalent height on the Grand Transect is about 35 million years old. So those samples have come through that closure temperature window and from greater depth more recently. And we see the same thing in the canyons. So our youngest samples, we've been doing incision of the canyons, and once again, I'm going to show this data tomorrow, but Moran Canyon has the youngest incision age, the most incision. So it was like 9 million years at the bottom of that canyon. So there's been a lot of incision there. Between Moran and Lee Canyon, there's been a lot of incision there.
What's causing the incision?
It seems to be the glaciers. Those are the two most well-developed glacial valleys in the range. I mean, except for the ones that are on the Idaho side. So they're incredible. They're so much bigger than the others. I mean, Cascade is pretty developed as well, but once you go through Cascade, there's not really another one that's similar to Cascade, Lee, and Moran, and maybe that explains Mount Moran. Maybe Mount Moran has fallen down a lot faster because it's bracketed by the two biggest glacial valleys in the park. But there's a lot of complexities in that, though. It's not simple.
It's also topped by flathead sandstone.
Yeah.
Which is,
The Paleozoic, yeah.
Yeah.
The last 3 feet of it.
But you don't find any of that on the Grand, of course.
No, that's right, that dome is arched. So something I didn't show that we're just now getting into, these inverse thermal history models, I showed you the last 30 million years. Ours go back 90, and there's a crazy laramide story in there too. So the architecture of all this stratigraphy prior to the Teton Fault getting going we think is really complicated, and we're just now starting to analyze that data, but it's really interesting. Yes.
How do you determine where you locate the sample that you take? Do you look for apatite, or do you just
every year I come out here and I tell the students, you should get this lithology because it has the best apatite in it, and then we go back and it's what my colleague at Illinois calls crapatite. It's pretty horrible. The only thing I've learned about picking lithologies is that whatever I pick is probably not going to be the best one, and I'm going to have to go back and get another rock. Most of the igneous rocks tend to be really good. These are very old rocks, so these apatites are probably multi-cycle. So we have, paranices, the really old metamorphic rocks derived from sedimentary rocks. Those apatites have been through a lot. Our apatites are really rough. Most studies will collect just a few kilos of rock to get the samples they need. We collect 10 for our samples, which is really horrible for our students and for our backs as well. But we collect about 10 kilos, and out of that 10 kilos, we end up with 5 to 10 apatite grains, tiny little apatite grains to analyze. Yep.
What was the total displacement again?
It's somewhere between 9 and 12, we think, at Mount Moran, 9 and 12 kilometers.
Okay. And that's based on the time and the rate that it goes up?
Mm-hmm. Yeah, our models take into account cooling rate and everything.
How deep would the sediments be then?
In the valley?
No.
5-6 kilometers maybe.
Okay.
Thickness maybe. I'd love to get. I would do a lot of work to get a major seismic line shot across this. I think I wanted to see what the Cenozoic section and the deeper sections look like here for a long time.
Have other people studied and theorized what that is?
There's been a whole bunch of studies. People use the angles of the tuff, the rotation of the tuffs, to figure out the displacement. People have used. I remember a study that said, well, the Teton Range can't be this old. It was a really good study by a woman that does pollen studies. And she was looking at how the pollen gets dispersed and whether or not the Teton Range gets in the way. And all of these things give different estimates. We just really don't know. This footwall uplift method is the first method we've had to date the footwall uplift component and to sort of come up with a magnitude of the footwall uplift component, but we still don't know what that hanging wall component is, and so we're using models to make our best guess, and there's some hair on that. I'll be the first to admit it. Yes, sir.
What do you think the probability is that the Teton Fault's related to the Gannett Fault, the fault there that's on the east side of the Gallatin Range?
Oh, the Gallatin Range. I mean, if we didn't suspect they might have a relation, we certainly wouldn't have collected a transect up it. It turned out to be the hardest transect we collected. Apparently that area is closed in the summer for all the grizzly bears that are there, and it's like a 17-mile one-way walk, and I happened to miss that day. But we suspected it just because of looking at a map, it sure looks like it's a long trend, and maybe there's this larger lineament and the two things used to link up. I don't know, probability, I don't know. I feel a little nervous stepping into the probability pool, but I think it's possible.
Yeah, well, most geologists that would look at a map would probably say those two things hook up.
Yeah, and it's fair to say that our projection that I showed you was a projection that was just a straight line, keeping it going, right? If that thing just curves a little bit, then you can go find your way over to the Gallatin Range, and like I said, the uplift age seems to be about the same, almost identical actually. But that could also be because the basin range was really getting going at that time. A lot of extension. Yes?
So Ryan, how is the regional uplift of the western U.S., the entire western half of the Teton, incorporated into your analysis of the chronology?
Well, I think that's going to come into the longer story. So my colleague Willie Gunther is working on what he calls the Great Unconformity and then into the west. So he's very interested in the Laramide uplift, and he's doing it over a much larger space. And I think once we know what that Laramide story is, we're going to have a lot better handle on what exactly happened here.
That regional uplift is way after the Laramide though.
Okay, maybe I'm confused then. What's your...
The whole western U.S. is very high, anomalously high elevation.
Oh, right. Okay. You mean sort of the intermountain zone, right? Like Colorado Plateau and all this stuff moving north. Is that what you're...
West from Mississippi west, basically.
Yeah, but I think it's probably in the background for our analyses because we're talking about so much exhumation, 3-4 kilometers. I mean, you could probably knock a kilometer off of it for some sort of regional uplift, but it's probably not going to be 5 or 6. So, and this is part of that analysis, like I said, that Willie's doing of the Great Unconformity across America. And so I don't know, we'll see. We'll be open to learning new things.
Before you did it here, can you say a little bit about tomorrow? And you all know it's at the Senior Center, and we have Ryan will be talking tomorrow, and tell them a little bit about what you're going to cover tomorrow.
Sure. Yeah, so we're starting to branch out into a lot more studies that look at some of the questions you were asking about Mount Moran and about the Grand Teton and about erosion that happens in the range. And specifically, one of the big problems in tectonics and geomorphology right now is whether or not climate can control tectonics, or whether or not tectonics are always in control and climate is simply responding to that. And also how the different climate mechanisms like rivers versus glaciers can erode systems with different efficiencies. And so there's been a whole lot of work being done in the Himalayas on this problem, but it's a really complicated system. And so we've got a whole new project going here where we're looking at trying to answer some of these questions using the Teton Range as a natural laboratory. We're shooting seismic, we're doing incision studies, we're using LiDAR, we're doing all sorts of things to get at these problems. So I'll be talking about that project is very much in its infancy. It's not nearly as mature as this one, but I'll be showing some of that seismic data from last year's shoot and talking about some of the conclusions that my students have come up with in the first couple of years.
What time is that? It's at noon at the Senior Center. He'll actually start talking about 12:15. You can have lunch. I think most of us would qualify for the $4 lunch. And we have a whole section all to ourselves, so and we can fit you all in.
All right. Yes.
Projecting the date for the beginning of the Teton Fault of 16 million instead of what usually thought of as 8 or so, that would put it about the time that they estimate the plume for the Yellowstone. Would that mean that the basin and range kind of all began to form when that plume began to form the hot spots?
I mean, it's a great observation. It's tough. I wouldn't have an answer to that question. I'm still not convinced that I understand what causes basin and range extension. So I think that's a really challenging topic, but it's interesting to think about. I mean, this age sort of puts our fault more in line with a lot of the other basin and range faults in the region, and it sort of solidifies the idea that this is truly a basin and range fault. Now, it may have some interactions with Yellowstone late, but it's a basin and range fault early in its history, we think.
All right, so hope everybody enjoyed the talk. Can you Ryan, a little token of our appreciation.
Man. Okay, thank you.
So you can all unmute your phones now, and if we could do the usual chair drill, please, and move the chairs to either side of the room. Appreciate it, and hope to see everybody tomorrow. Thank you.